Welcome to this video lesson. Today we will be looking at vector and parametric equations for planes. You should be familiar with 3D vectors and 3D lines for this lesson. Adding a line perpendicular to another line will add dimensions to it, up to 3 dimensions. So starting with a dot that's 0 dimension, we add a line to it 1 dimension, we add a line perpendicular to it that's 2 dimension, and we add another line perpendicular to those and we get to 3 dimensions. In this case, the 2 dimension is a plane. This is a flat surface that extends forever and has 0 thickness. There are different ways of defining a plane. Today we're going to focus on one that requires 2 different vectors. These vectors are non-parallel to each other, but they are parallel to the plane. They also lie on the plane as well. Let's imagine that we have a 3-dimensional coordinate system, and here we have 2 points A and R that lie on the plane, and they can be connected through 2 vectors B and C. In this case, vector AR is equal to the direction vector B multiplied by some parameter, in this case t, plus direction vector C multiplied by some parameter, let's call that lambda. Now let's simplify these by representing everything using position vectors. So we're going to add position vector A and R, which originate at the origin and terminate at point A and R. And based on this, vector OR is going to equal to vector OA plus vector AR. And if we rearrange this, we will get that vector AR is equal to vector OR minus OA. We sub that into the equation that we have and we rearrange it for OR. And we end up getting that our position vector R is going to equal to position vector A plus t multiplied by direction vector B plus lambda multiplied by direction vector C. This defines the vector equation of a plane which contains points A and R, so those 2 are points that are on the plane, and the direction vectors B and C are 2 direction vectors that are non-parallel, so they're not parallel to each other. However, they are parallel to the plane, helping us figure out the direction that the plane is going to. T and lambda here are real values, and they are just parameters that help us scale the direction vectors B and C in order to find point R. We can change this vector equation into parametric equation by breaking it down into x, y, and z components for all the vectors. So the position vector R's component are going to equal to position vector A's component plus t times the direction vector B's components plus lambda multiplied by the direction vector C's components. The summary of this video is fast forwarded here, so if you need to pause and write any of the information down, please feel free to do so. And now we are going to look at an example. In this question, we want to determine the equation of a plane that contains the 2 parallel lines shown. Note that when we're talking about vectors B and C, or the 2 vectors that help us figure out the direction of the plane, they don't necessarily need to be on the plane itself. We usually just need a line or 2 points, and those 2 directions kind of give us an understanding of which direction the plane is going at. In this case though, it says that the plane does contain the 2 parallel lines. Because vectors B and C need to be non-parallel lines that show us the direction, we can take one of the direction vectors from one of these lines, but for the other one we have to find it. We're going to start off by kind of talking about what we're going to use. We can use one of the points from either R1 or R2, the initial points. We are going to use the direction vector B, and we're going to simplify it because it's a direction vector and it's multiplied by t. We don't actually need to use -6, -3, 6. We are going to divide it by 3 and use -2, -1, and 2. And as I said before, note that the two lines are parallel, and we can check that because 4 to -4 is a multiply of vector b. It's -2 times that. Now, we do need a second vector because those two lines are parallel, and we need another direction vector, and we know that points 0, 1, 3 from R1 and -4, 5 and -4 from R2 are actually on our plane because the question says that these two lines are on the plane. So we can use those 2 points to come up with the other direction vector. This vector is going to be a1, a2, and we are going to take all the coordinates of a2 and subtract them by all the coordinates of point a1. And once we have that, we will get components -4, 4, and -7. And this will represent our direction vector c. Now that we have both of these direction vectors were set, our equation is going to be one of the points. We can use 0, 1, 3 or -4, 5, -4 plus t times one of the direction vector, -2, -1, 2 plus lambda multiplied by the other direction vector, in this case -4, 4, and -7. Note that the direction vectors can be simplified, but our points need to stay what they are, so they can't be simplified. So the 0, 1, 3 has to stay the same. I have prepared one practice question for you folks to try out on your own, and I will try to post a solution to this as soon as I can on a separate video. I hope that this video was helpful in giving you an introduction to planes and the parametric and vector equations. The next day we are going to derive another form of equation for planes, which is actually a very, very useful form. Thank you for watching.